So, as I've said, my talk today is about confocal microscopy imaging of originally microspheres, but now some more interesting defects that we've seen in liquid crystals. And the work's been conducted by myself and Professor Roy Samples from the Electromagnetic Materials Group in the School of Physics at the University of Exeter in the UK. So the motivation behind this work really stems from the fact that for the past 20 years at Exeter we've been developing powerful optical waveguide characterization techniques for probing in detail the 1D director structure in liquid crystal cells which vary between the substrates only, so one dimension. But as practical devices are now moving to 2D and even 3D structures, such as in xenophore bisople devices and the PABM cells produced by Hewlett-Packard, the optical techniques we use must follow suit because our original characterization techniques rely on beam spot size of a few hundred microns. So the technique we're using is fluorescent confocal polarising microscopy. We've had a few talks today mentioning this. Lisa Hurst earlier talking about their visual applications in biological studies, and also in the previous talk as well highlighting some of the features. The key thing is that we can image structures on a sub-micron scale, so we're talking around 0.5 microns or so, and these are quite readily resolvable, and why we're interested in using these for our liquid crystal structures. In these structures, we've selectively doped the liquid crystal we're using for very low concentrations, so we're talking 0.01% of a fluorescent dye, and by recording the fluorescence intensity as a function of position, when we excite the dye with polarized light, we can then actually determine the director's structure. So this is just a brief schematic of what your typical dye-doped liquid crystal would look like. So the green molecules are your liquid crystal, and the red is shown with the dyes. The crucial thing is we're using an anisomeric dye, which is rod-shaped, so it tends to align with the liquid crystal. So it's mimicking the structure of the liquid crystal through the cell. I want to stress at this point, it's always the dye that we're actually imaging, but we carefully select it so that it has an orbit parameter which is comparable with the liquid crystal and also immiscible with the liquid crystal. And we're also having to use the liquid crystal with a low bar refringent, again as referred to earlier, so that we're not getting focusing at two different points. So this has previously been used to explore a number of different types of structures, particularly by our co-chair of the conference here, Ivan Smolik, at Kent State. They've looked at things like Carnot wedges and biaxial synectics. So the way that we can actually determine how our dye and therefore our director is aligned is by considering the intensity of the fluorescent light that we get back from our dye molecule. So by some simple optics, and you'll see in a moment in my next slide, we can work out that the intensity of our light is proportional to cos to the fourth beta of the angle between the polarizer and the dye axis. So we've got a nice planar cell here with our polarization perfectly parallel to our dye axis. We're going to get a maximal intensity of emitted light. If we rotate the cell for 90 degrees, we're now excited along the ordinary axis, so therefore we're going to get a minimal intensity, and also the same for, in our case, homeotropic alignment as well. So the dye that we're actually, region of the dye we're exciting is within this very small sub-micron cube voxel, so a 3D pixel, of our liquid crystal. Because we're using a confocal microscope, only the light emitted from that particular voxel of interest is going to actually be detected. And this is measuring the dye fluorescence in a position of, as a function of position, is going to actually give us our director structure. So this is a very brief schematic of our optical fluorescent confocal polarising microscope. The incident light comes from an argon ion laser. For the particular dye we're using, it's 488 nanometers. And the light comes in, so it's a collimated beam that comes in, passes through the polarizer, excites our dye, and then the fluorescent light goes back through the polarizer, and then the lens and the pinhole focus it onto our photomultiplied tube so we can detect the intensity at that specific point in the sample. The purpose of the pinhole here is to actually provide us the spatial resolution, so it's the lens and the pinholes are arranged in such a way that only the light emitted from this voxel is actually able to pass through the pinhole and is detected. Anything from outside this region is not in focus of the pinhole, so you get a very low intensity, so it doesn't really affect our collected fluorescent light intensity. So this is the first of the cells that we looked at. This is actually a very simple study of our dye, BTBP, added to a Zedolite 2806, which is a Merck compound, which is specifically chosen because of its very low optical birefringence. We looked at about 1% of 5 micron glass beads, aligning it in a thin planar cell. So using red polyionized aligners and then cover slip glass on one surface where our light is actually coming in, as this prevents any distortions from the glass in our confocal system. We're actually using it in an inverted microscope lead. The region we're actually looking at was originally around 25 microns square, stepping through in the Z plane in set about 0.25 microns over a depth of 30 microns. And of course, we collect the intensity as a function of X, Y, and Z position. So I thought I'd show you just a few samples of the sort of X, Y scans that we would get. So in actual fact, we end up with about 120 slices this particular cell, but I've just picked out a few. So we start off focusing into the glass, so it's completely black, there's no fluorescence in the glass, so we get no signal. And as we step up through the cell, we start to excite the actual bead, which is, in our case, the polarization of the light is parallel to the rubbing direction, so we're getting a nice bright signal. You can see as we're getting up through the cell, this is the location of our bead, because it's black and the glass doesn't actually fluoresce, therefore it looks like a dark patch. You can actually see we're starting to see some kind of defect at the edges. Again, stepping back up through the cell, we're now moving away from the bead and back into the upper glass. So if we actually recolour this to make it slightly easier to see our maximum and minimum intensities here. So red is where we get maximum intensity, so our director is aligned parallel to our polarization, whereas the blue, we've either got no fluorescence or the dye is perpendicular to it. You can see we've got a nice bright, nice dark blue spot in the centre where we've got our bead, so we're looking approximately at the centre point of the bead. Planar aligned liquid crystal all around the edge, and then we're getting these sort of defects, or this sort of halo around the edge where the director is actually distorting when it's in contact with the bead. I want to stress that here we haven't got any treatment at all on the bead, it's just a glass bead, so we've got no preferential orientation around the bead. But you can see that we're actually getting a sort of a hotspot here. It's almost like rugby ball shapes in this direction here with this hotspot. So we're trying to rotating the polarization by 90 degrees. So we're now exciting the diode short axis, and again on the outside edges we've got uniformly aligned liquid crystal, presumably therefore aligned perpendicular to our polarization direction. But now you can see we've got these hotspots again in the same place as before, showing that because we're getting intensities independent of the polarization of the instant beam, it must indicate we've got some kind of melting or some kind of defects here. Again, for all the beads that we saw underneath the microscope, they were always in this orientation due to the symmetry actually being broken by the rubbing direction imposed on the cell. Now, the beauty of taking such XY stacks, as people have gone into before, is that we can actually use image processing software to generate a cross-section through the cell. So using simple software, we can then obtain images of our beads, again from the two different polarizations. Here we've got polarization parallel to the rubbing direction, and here we're perpendicular. Again, you can see we've got our defects, and these are actually spanning quite a distance in the Z direction. These defects are really curving around by the size of the glass beads. At the top and bottom it's just black because we're focused in the glass. But you notice actually that the resolution we get in the Z direction is a lot poorer than what we were seeing in the XY, and this is due to the point spread function, or mainly due to the point spread function of our confocal system being a lot greater in the Z direction. So after looking at the beads, we decided to then see what other sort of defects we could look for, what other sort of structures. And so we decided to actually look at in-plane cells. So here's a schematic of the sort of stuff we're looking at. This time we've got no beads inside the cell, we're purely producing the defects by applying electric fields. We've got two silver electrodes separated, depending on the study, between about 25 and 125 microns. The electrodes were produced by putting down an optical fibre as a mask and just thermally evaporated about 100 nanometers of silver. Around 20 microns in thickness of liquid crystal, again with our rubber polyarmor to align it. And we decided to have a look at some polysteric structures, specifically two different types, one with a negative delta epsilon and one with positive dielectric anisotropy. So the negative one was 6608, the positive 2293, both were again available from Merck. And we've doped it with low concentration of CB15 to produce a 5 micron pitch roughly in each case. So we're collecting the images, again, in the XY plane, in this case in about 0.2 micron steps, and applying different in-plane voltages to see what distortions we could produce. So this is just at 0 volts, just to give you an idea of what you're actually looking at here. Sometimes it's a bit difficult to see on the screen. We've got our cholesteric cell here. At the top and the bottom we've actually got glass, and the dotted line is showing us where our silver electrodes are. You're going to have to use your imagination and pretend that the one bit is black, because one of the problems of focusing using the confocal microscope into a point that's actually below an optically thick silver mirror is the light gets reflected back up into the system, so you end up with this sort of false image, which is actually come from a point equidistant above the electrode. And that's a particularly interesting optical technique, but will be a whole different presentation, so we're going to ignore anything below these lines. What you can see here, there's this banded structure, which is showing us a cholesteric structure. So over a bright stripe, it's where our polarization direction and our director are collinear, and where it's darker is where they're actually perpendicular. And so we get this sort of modulation in our intensity here. The reason why we don't see this nice sharp variations is because, as I mentioned before, we've got a point spread function in the cell which actually increases as we're going through the cell up to about a micron or so down the bottom here. But we can still work out, so we can still certainly see we've got a cholesteric pitch and of the order of around 5 microns. So this is what we see as we start applying the voltage. So at 0 volts we've got our stripe structure, and then upwards it stays like that until we get to around 14, 15 volts. Then we start to see this sort of distortion in the cholesteric layers. So it takes a little while to form this. We allowed it to settle for about 10 minutes. But you can see that although we're maintaining our cholesteric bands, we are getting this wonderful sort of bending of our cholesteric layers. And at the very centre, we've got high fields. We're actually unwinding the helix completely. And I should stress this is the positive material that we're looking at now. So the director is going to try and align with the in-plane field. You get a little higher, and we'll unwind more of the helix, but we're also now getting this sort of rather messy areas either side of the electrode. And as we carry on, you can see this carries on. So we've unwound at the centre, and on the edges we're actually we're having formed here a cholesteric structure where the helix is actually tilted through 90 degrees. So the helix outside the electrode region is now tilted over. It's maintaining around a 5 micron pitch, but it's taking an awful long time to actually stabilise. So these images are taken up for about 20-25 minutes. And you can still see defects zipping through the cell parallel to the electrodes during that time. So this is where it's slightly smeared out, because it takes 3 or 4 minutes to get a full 3D image from this scanning technique, so that it's sort of varies slightly as we've started the scan. You can definitely see that we've nicely unwound the helix in the centre now, and we are getting a cholesteric structure on the outside. Try this again with a negative material. So again, we've got a 5 micron nice and striped pitch at 0 volts. As we start applying the field, we've got a wider and we've got a lower delta epsilon on one modulus in the delta epsilon, and also a slightly larger in-plane gap. But you can see that we're getting this beautiful sort of distorted structure here in our cell at 40 volts. So we're actually maintaining our layers in virtually all the places and maintaining this 5 micron separation. But we're getting this sort of almost looks like a fingerprint in profile or in cross-section in the cell. This is actually quite stable. Once we applied the voltage, it then tended to stay there until we went up in voltage. So you can see now it's sort of sorting itself out. So it's now creating a cholesteric helix in the centre. And at 100 volts here, we've actually got a very nice 5 micron pitch cholesteric structure here. It's actually unwinding completely at the bottom here, where we've got the highest field. And also this highlights nicely what I said earlier about the point spread function being pretty poor in the Z direction, but in the XY direction you can actually see pretty clearly your distinction between your cholesteric pitches here. So showing that we've got a much narrower point spread function issue in the XY plane. So we can actually put this together as well, sort of showing you sort of 3D what we're seeing here. So these lines are actually formed by defects zipping along in this direction throughout the cell as these cholesteric helices form. And again, they seem pretty stable once they form. They seem to stay there until you remove the field. So we're now interested in understanding how these form, particularly interested in the positive materials of what we're getting this cholesteric structure on the outside. So using a very simple electric field modelling package from ANSA called HNSS, finite element modelling code, we can actually model what our electric fields are within the cell. So the colours are indicating how high in magnitude the fields are, and the arrows are indicating the actual field lines. So you can see that our bands and the way our cholesteric structures are distorting are actually generally following our field lines, and of course we're getting the higher fields at the bottom as you would expect. But it is nice to see how these kind of curves follow quite nicely our electric field lines. Also, actually, at the edges of the cell, we're getting quite reasonably strong field lines emerging perpendicular to our silver substrates right up in this direction. So again, that accounts for the the cholesteric pitch, which is extending in sort of tens of microns in this direction and that direction through the cell. So this is again the 2293 responding to the fields. So the last thing we want to do is actually model this. So using a very simple model, you can see straight away for considering the elastic energies of a cholesteric structure that because of the sign dependence on delta epsilon, when you've got a negative material, this equation is always going to be minimized with the helix lying parallel to the electric field, so that the cholesteric, so that the helix has to form in this direction, and the bits above the electrodes are just going to add sort of boundary conditions to our structure. Because actually for the positive material, it's actually easier, energetically favourable for it to actually completely align with the centre, and for the fields, stray fields at the edges here to actually cause it to tilt the helix over. So these stray fields in this particular case were extending over several tens of microns. It's something that may be important for the display industry, with pixels getting closer and closer together for high resolution devices. The effective stray fields can be considerable, and it's not until 3D imaging techniques like this and the other techniques that we've heard earlier today as well, mean that we can actually look inside and physically see what's going on inside this liquid crystal cell and what effect it actually has on director. And I just want to say that we're actually hoping then to do a more detailed analysis of this with collaborators at Case Western University in Ohio. So hopefully we'll get this completely sorted soon. So finally, then, just my conclusions. So I've shown you today that we can use fluorescent confocal polarizing microscopy to get high-resolution 3D imaging of liquid crystal structures. In particular, we can see direct distortions around objects that have been embedded in the liquid crystal, and we can resolve these on a sub-micron scale. And also the influence of stray fields and the influence of in-plane fields as well can be imaged in detail for different director alignments. So finally, I'd just like to acknowledge George Lawrence and Steph Confocal from the University of Exeter in the UK for helping this project, and Tim Atherton at Case Western Reserve as well. Also EPSRC in the UK for funding the work, and the organisers of the conference for allowing me a travel scholarship to come here today. Thank you for your attention.
We have time for a question or two.
Yeah, how could one interpret the sort of loop shape on the first time I've ever seen the loop shape on the fringes that are going vertical like that?
Sorry, on this?
Yeah, the image, the yellow, the fringes have a sort of a closed loop.
It is interesting. It's parallel aligned at the surface. So it's rubber polyamide, so it's medium anchoring, but it does look really neat under the microscope. Actually, you do actually see these stripes. It is actually physically, so where it's black, you've actually tilted the direction through 90 degrees up there. Why it does that, why it's periodic, I assume it's because we've got this 5 micron, this dopant to make it cholesteric, so you're getting quite a playoff between your surface anchoring energy and your elastic energy within the bulb. So it's something that we're going to have to actually put into our models, try and account for this. It's going to be tricky to model, but
So time for one more question. So I was curious whether or not
I don't know how large the dielectric differences are at DC for these sorts of things, and I was wondering if you needed to take into account the director field in order to be able to calculate the electric field.
So I think for what we're looking at, I think it should be reasonably okay, I think, but certainly for the modelling that we've done for when we've actually modeled the electric field within the cell, and that we just assumed it was an anisotropic medium, and that seemed to actually cover it. Okay, so I think for a real determinant, yes, we would certainly need to prove anisotropic that this is the first approximation. It seems to be okay.
Let's thank our speaker again.
So right after this session, we'll have our workshop dinner. It will be at the Millennium Hotel, where many of you stay. And everybody will need to pick up one drinking ticket, which you can take at the registration desk. And then we will simply walk to Millennium Hotel. It's a very short walking distance. So I look forward to seeing you at the reception at the Millennium Hotel.
The workshop is open to public and web in the future, right? Correct. So they asked me to not to open to public
So not to post it?
No.
At any time?
Not at all.
Okay.
Only for my
Yeah, sure.
You have like data that you don't want known? It's just like not published yet? But what about 6 months from now?
It's up to open public for my presentation. I'm a friend of people.
Okay. You mean?
Yeah.
No problem.
Oh yeah, let's talk about that. Polarising. Like just what I had said.
Yes.
Maybe you could leave all the talks to later.
Okay, I mean, I still have to get those two right there, so.
Okay.
Then I gotta. Okay, so I guess I should delete it. Because you don't want your presentation part of the archive.
Oh.
Okay, here's my presentation. The only thing is there are some stuff that I do need to take it out from here. There's some extra.
Here, I'll let you do that because this doesn't have PowerPoint on it.
Doesn't have. How about if I work tonight and my roommate has the computer, so I can bring it tomorrow?
Okay, that'll work.
That will work too.
What was the name of your presentation? I was talking about.
Oh, okay.
Crystal too.
Actually, it's still on the thumb drive there, so.
how we will do the new design. This is nice, so we will erase this one. How copy? Cut. So it should be good.
So could I have your name? Jason. And you're working with the people?
Well, I'm the web designer for ICAM. So I started one of the sponsors to provide the web testing.
You are responsible for the organization of the how to public give presentation.
Okay, great, no problem.